Hello class, this is a video tutorial on exponential functions. In this video we'll be looking at the stage 6 form of this topic. So functions of the form y equals n to the power of x, and this is only true if n does not equal 1. So 2 to the power of x, 3 to the power of x, even half to the power of x, or even negative 5 to the power of x. These are known as exponential functions. The critical features that we should know are as follows. We have a y-intercept, always at 0, 1. This is only true for the basic form, n to the power of x. So it will always intercept at 0, 1. So this is also known as the initial value. When x equals 1, the y value there is always equal to the base that it has. It has a horizontal asymptote at y equals 0. It's hard to see here, but it's going along the x-axis. And it is at an increasing rate of change. This means that as this increases, it's getting steeper and steeper at all times. So not only is it increasing, the rate it is increasing by is also increasing. So here's a few graphs of these. Here is 2 to the power of x. Notice how it's passing through 0, 1. And at 1, it's equal to the base that it has. At y equals 3 to the power of x, once again, it's intersecting at 0, 1. At x equals 1, y is equal to 3, which is the base. I'm pretty sure you're getting the idea here. At 0, 1, at x equals 1, y is equal to 4. Note as the base of the exponent increases, so this one here, the graph becomes more steep. So it's becoming steeper and steeper as the base increases. Now here are the transformations of the exponential function. These are the ones we should know and know the appearance of. If we reflect along the y-axis, so n to the power of negative x, instead of it going upwards like this, it is now going downwards like so. It's more appropriate actually to have the arrow going this way, so it's decreasing. You can reflect along the x-axis when we have a negative n to the power of x, so this is what it is, and from what it was, it would look something like that. A vertical translation, so we have n to the power of x plus k, so plus or minus any value k. All this does, it moves the entire thing vertically up or down. So originally the asymptote was here, and the graph looks something like, was here, and the graph looks something like this. But now because it's plus k, the entire graph has just moved upwards. A horizontal translation, these ones we won't cover too much, but this one's pretty hard to graph, whereas the original would be something like this. It has now moved everything to the right by the value of h. Once again, this one we don't cover too much at this stage, but these three we ought to understand the appearance of. Okay, so when graphing exponential functions, the critical points covered should always be noted. So we should always think about where the asymptote is, where the y-intercept is, and if we can, where the x value, or where the y value is when x equals 1. Well, exponential functions are often used to graph or model population growth. So let's just go straight into an application of this. And here we are. So the weight of a mold colony in grams is modeled with a function m equals 0.5 times 2 to the power of t. In case you don't see it, the exponential function looks like this: 0.5 times 2 to the power of x. So the component 2 to the power of x, this is the exponential component. It's just merely being multiplied by half. Okay, so now what is the initial value or the initial weight of the mold colony? Whenever we hear this idea of initial weight, what we're looking for is when t is equal to 0. So all we have to do is substitute y equals 0.5 times 2. Now instead of t, we let t equal 0. You can plug this into a calculator, or if you understand exponentials, you'll know that 2 to the power of 0, 2 to the power of 0 is 1. 0.5 times 1 is 0.5. So the initial weight of this is 0.5 grams. Oh, sorry. Instead of y, it should really have been m. So there we go. What is the weight of the colony after 1 hour? Well, since t is in hours, after 1 hour, all we're doing is just substituting t is equal to 1 for this. So t is equal to 1, we get m is equal to 0.5, 2 to the power of 1. Well, we know that y equals 2 to the power of 1. Using what we know from the feature, when x is equal to 1, the value is always equal to the base. So in this case, the base of the exponential is 2, but it's being multiplied by 0.5. So really it's 0.5 times 2, which is 1. So the weight of this is 1 gram after an hour. At 5.5 hours, all we're really doing is substituting t equals 5.5. So we get m is equal to 0.5, 2 to the power of 5.5. This time, it's much easier if we just use a calculator for this. And there we have it. So it's approximately, let's just round straight away to 2 decimal places, 22.63 grams. At 8 hours, that's nice and straightforward. T equals 8, m equals 0.5, 2 to the power of 8. We get 128 grams. So now, by graphing the function, approximate how long it will take for the colony to weigh 1 kilogram. So in this case, we're being told that the mass is 1 kilogram, but always be mindful in questions such as these, because the colony is being weighed in grams, the value for m we're looking for is 1,000. At this stage, we don't have techniques to solve this, because if we were to make this into an equation, we get 0.52 to the power of t equals 1,000. This is an equation that we should be able to solve much later. But using the graph, when m, or in this case y, is equal to 1,000, like this, all we're doing is we're looking at the graph and looking at what value of x, or in this case t, is giving us 1,000. So previously it says at 8 hours, when x is equal to 8, or when t is equal to 8, we're giving m is 128. So if we had m here, sorry, if we had t equals 8, this will give us 128. But now we're being told that we're given the y value, and we now need to look for the x value. So this is what we're doing here using the graph. So looking here, it looks to be almost 11. It's very hard to approximate that properly. So from the graph, we can approximate that t is equal to 10.9 from the looks of it, 10.99. Or just say 10.9. Let's take a look at what happens when we substitute that in. So 0.5 times 2 to the power of 10.9. 955. Let's see if we can get a little bit closer. 10.99. That's a bit too much. So 98. Whoops. 10.98. Oh, getting closer. 10.97. Getting even closer. Really all we're doing now is guessing and checking the answer that we get. Once again, that's too small. 10.969. We could keep going, but let's just approximate it to 10. T is approximately to 10.969 is too much. 968. I really want to get a close estimation here. 968. And there we have it. So I hope that has given you an insight into the shape of the exponential function, as well as how it might be used to model real-life scenarios. Hope to see you in the next video. Best of luck.